Picture this. Somewhere in the cold, silent expanses between stars, the most widespread form of ice in the entire universe is quietly shaping the origins of planets, and possibly the very beginnings of life itself. For nearly a full century, scientists imagined this cosmic ice as a simple, glass-like, shapeless substance. It was believed to be the perfect hiding place for life's essential ingredients as they journeyed through interstellar space. But what if this entire foundation was built on a misunderstanding? What if, instead, this frozen matter is a far more intricate and mysterious material? One whose secret internal structure could not only change our understanding of space, but also revolutionize technology on Earth and rewrite the story of how life arose. Let's kick things off with a crash course in what space ice is and why it truly matters. When you picture ice, you probably think of the hexagonal crystals in a snowflake. Or perhaps the solid cubes clinking in a glass of water. That's what scientists call crystalline ice, the type that forms in Earth's relatively warm conditions. Here, water molecules have the energy to arrange themselves into neat, repeating patterns. But the rules are completely different in the vacuum of space. Among comets, icy moons, and swirling clouds of dust where new stars are born, water freezes under extreme cold, often hundreds of degrees below what we would call freezing. In these conditions, water molecules lack the energy to line up tidily. For almost 100 years, the prevailing view among scientists was that water in space becomes locked into a chaotic, disordered form known as low-density, amorphous ice. The first glimpse of this strange ice came in the early 20th century, when researchers condensed water vapor onto metal plates chilled to well below -100 degrees centigrade. What they found was a kind of glassy, structureless ice, a frozen jumble of molecules. This model seemed to explain a lot. It accounted for the behavior of comets, the way planets accumulate mass in the disks surrounding newborn stars, and, most tantalizingly, how simple molecules like amino acids, the building blocks of life, could be trapped inside ice grains and ferried across the cosmos. According to the influential panspermia theory, perhaps even the first seeds of life on Earth arrived inside these cosmic ice shells, shielded from the lethal radiation and temperature swings of deep space. But the scientific story has taken a dramatic turn. In recent years, groundbreaking research led by Dr. Michael B. Davies and his colleagues at University College London and the University of Cambridge has upended this tidy narrative. Using cutting-edge computer simulations and painstaking laboratory experiments, these researchers peered into the atomic structure of space ice. What they found was astonishing. Space ice is not just a random, chaotic mass. Instead, hidden within its glassy form are countless numbers of tiny crystals, each one only a few nanometers across, roughly the width of a single strand of DNA. These minuscule crystals are like secret islands of order, floating in an otherwise disorderly sea. As Dr. Davies explains, we now have a good idea of what the most common form of ice in the universe looks like at an atomic level. And that idea is anything but simple. Space ice, far from being a uniform, perfect sponge for life's building blocks, is a patchwork, a dynamic composite of amorphous regions and crystalline domains. Each influences the behavior of water and the molecules that it can carry. This seemingly small detail carries seismic implications for science, technology, and our search for life beyond Earth. Why does this matter so much? For decades, space ice was seen as the ultimate cosmic delivery truck, a material riddled with nooks and crannies where complex organic molecules could nestle, protected from the harshest conditions in the universe. This was a cornerstone of the panspermia hypothesis, which posits that the precursors of life did not arise on Earth, but instead arrived on comets or meteorites, preserved by the random, porous structure of amorphous ice. Yet, the new findings challenge this comforting narrative. According to the latest studies, the presence of crystalline regions within the ice means there is far less space for those vital molecules to hide. As Dr. Davies points out, the presence of crystals in space ice reduces its capacity to carry prebiotic molecules. In other words, the more ordered the ice becomes, the fewer secret pockets remain for amino acids, sugars, or other organic compounds to embed themselves. Dr. Jennifer Blank of NASA Ames underscores this, stating, "Understanding the composition of space ice is crucial for determining the potential for life beyond Earth." But all hope is not lost for cosmic hitchhikers. Even within this patchwork structure, there remain amorphous regions, tiny pockets of disorder, where life's essential ingredients might still be sheltered, at least temporarily. The research team discovered that the balance between crystalline and amorphous regions depends on how the ice forms. If water vapor freezes rapidly, as it does on the dust grains drifting between stars, it is more likely to stay in a disordered state. If it cools more slowly, or is exposed to bursts of radiation or heat, more crystals form. This means every grain of space ice has its own unique history, shaped by its journey through space and the environments it encounters. The result: its ability to carry the seeds of life is far from uniform. This breakthrough also transforms our understanding of how planets and moons come together. In the dense, frigid disks of dust and gas orbiting young stars, grains of ice act as the glue binding tiny particles together, eventually forming pebbles, planetesimals, and in time, entire planets. The way water molecules are arranged inside these grains determines how sticky they are, how well they trap other molecules, and even how they interact with cosmic radiation. In other words, the hidden crystals inside space ice may be quietly guiding the formation of planetary systems, determining which planets form, where they emerge, and what materials they are built from. The implications stretch even further. Amorphous materials, such as the glassy ice found in space, are at the very heart of modern technology here on Earth. Fiber optic cables, which transmit the world's data at the speed of light, rely on perfectly amorphous glass to prevent signal distortion. If, as this new research suggests, even the most carefully manufactured amorphous materials secretly contain tiny crystals, then there is a new frontier for materials science to explore. Professor Christoph Salzmann from University College London Chemistry remarks, "If we can remove these crystals, this will improve their performance. Imagine a world with faster, clearer internet connections, more sensitive scientific instruments, or even revolutionary advances in quantum computing, all made possible by understanding the hidden structure of materials we once thought we fully understood." This is not just abstract theory. Around the globe, space agencies and research institutions are racing to unlock the secrets of icy bodies in our solar system and beyond. NASA's Europa Clipper mission, scheduled to launch in the middle of the 2020s, will explore Jupiter's moon Europa, a world covered in ice, with a tantalizing ocean hidden underneath. The mission's advanced instruments will analyze Europa's surface composition and structure, searching for clues about its potential to support life. Meanwhile, NASA's Prime 1 mission, planned for the near future, will attempt to extract water ice from the moon's south pole, drilling into regions that never see sunlight. The European Space Agency's Comet Interceptor will, for the first time, visit a pristine, untouched comet, providing invaluable data on how space ice forms and evolves. These missions are far more than scientific curiosity. They lay the groundwork for humanity's future in space. Mapping lunar ice deposits, for instance, is absolutely vital for future astronauts, who will depend on water for drinking, fuel, and even growing food. Dr. Paul Lucy from the University of Hawaii emphasizes, mapping lunar ice deposits is critical for future resource utilization. NASA's Viper rover will soon be mapping the distribution of water ice in the moon's permanently shadowed regions, helping to chart the resources needed for long-term lunar bases and, eventually, missions to Mars. China's Change 7 mission, aiming to explore the lunar South Pole, will further our understanding of these invaluable resources. But our quest for knowledge does not end at the moon or Europa. Researchers at the SETI Institute are investigating whether the unique environment inside space ice could actually foster or protect microbial life. At the University of Leiden, scientists have shown that when ice is bombarded by cosmic radiation, complex organic molecules can form, potentially creating the very precursors of life in places we once thought utterly inhospitable. In fact, a study published in Nature Astronomy discovered that the crystalline structure of ice on Saturn's moon Enceladus plays a key role in the spectacular geysers that erupt from its surface, blasting water and organic molecules into space. These findings suggest that the interplay between ice structure and environmental conditions could be central to the emergence of life throughout the universe. Meanwhile, the James Webb Space Telescope, the most powerful observatory ever launched, is peering deep into star-forming regions across our galaxy, analyzing the grains of ice that float within them. By studying the way these grains scatter and absorb light, astronomers can deduce their structure, composition, and even their temperature, unlocking secrets that have been frozen for billions of years. The telescope's findings may provide crucial insights into the origins of water and organic molecules, not just on Earth, but everywhere in the universe. Let's zoom out and consider the even bigger picture. The discovery that space ice is partly crystalline, not purely amorphous, forces scientists to rethink many long-held assumptions. It means that every icy world we have studied, every comet, every moon, every frigid dust cloud, is more complex than we once imagined. It suggests that the recipe for life is more fragile, more contingent than previously believed, and it reveals that the materials powering our most sophisticated technologies may still harbor surprises with the potential to reshape the future. But this is also a story of scientific humility and relentless curiosity. For nearly a century, the model of amorphous space ice stood unchallenged, a foundation for textbooks, theories, and countless experiments. It took a combination of supercomputing, precise laboratory work, and a willingness to question the status quo to uncover the hidden crystals within. Professor Angelos Michaelides from the University of Cambridge states, "Water is the foundation of life as we know it, and understanding its many forms is crucial for science and technology alike." What does this mean for the future? First, it presents new challenges for the search for life beyond Earth. If the cosmic delivery trucks of the panspermia theory are not as spacious as once thought, we may need to consider alternative means by which life's building blocks travel between worlds. Perhaps only certain forms of ice, forged under specific conditions, are truly suitable for preserving complex molecules. Or, as missions like Europa Clipper and Comet Interceptor probe deeper, we may discover entirely new forms of ice with properties we have yet to imagine. Second, this knowledge will shape the next generation of materials here on Earth. If we can learn to control the size and distribution of nanocrystals within amorphous solids, we may unlock dramatic improvements in fiber optics, sensors, and quantum devices. The humble study of space ice could, in fact, fuel a technological revolution. Envision a world where internet speeds are not just 2 or 3 times faster, but 100 times faster. All because we learned to purify our glass as perfectly as the icy grains adrift in space. Third, these findings open up profound questions about the very nature of water. For centuries, water has resisted simple classification, manifesting in more than a dozen different forms of ice, including high-density, low-density, and, most recently, medium-density amorphous ice discovered in the early 2020s. This new form, with the same density as liquid water, would neither float nor sink if dropped into a glass. It would simply hover, as enigmatic as the universe itself. Such discoveries remind us that even the most familiar substances can still surprise us. Let's not overlook the practical implications for future explorers. For astronauts and off-world settlers, understanding the structure of space ice is essential. Not all ice deposits are created equal. Some may be easier to mine or process, while others could trap hazardous chemicals or sublimate rapidly under sunlight. The development of advanced extraction technologies, such as the Resolve payload system, depends on knowing exactly what kind of ice we are dealing with. As Astrotechnology points out, developing sustainable lunar resource extraction technologies is essential for long-term space exploration. The future of human presence on the Moon, Mars, and beyond will hinge on our mastery of these frosty resources. The story of space ice is, at its core, a tale about the unknown. It reminds us that even in the substances we think we understand, there are hidden depths and secrets waiting to be uncovered. It is a testament to the power of persistence, the value of skepticism, and the necessity of asking questions, even when the answers seem obvious. And it is about the sheer joy of being surprised by the universe, of finding out that the cosmos is even stranger, richer, and more beautiful than we dared to imagine. So what can you take away from all this? First, never underestimate the complexity of the world around you, whether it is a speck of ice drifting through space or the glass in your smartphone. For scientists, engineers, and curious minds everywhere, this is a call to keep probing deeper, to use every tool at our disposal, from telescopes and quantum computers to the timeless power of curiosity and skepticism. As new missions set their sights on the Moon, Mars, Europa, and beyond, we must expect the unexpected. Every sample collected, every spectrum analyzed, every icy grain returned to Earth could reveal a new chapter in the cosmic story of water, life, and the universe itself. And here is a remarkable statistic. Scientists estimate that low-density amorphous ice makes up the majority of all water ice in the universe. That means, out of all the ice on every comet, moon, and interstellar dust grain, most of it is this enigmatic, partly crystalline material. It is present in the Oort cloud at the edge of our solar system, in the rings of Saturn, and in the dense molecular clouds where new stars are born. The sheer scale of this cosmic ice is staggering. It shapes the chemistry of galaxies and the fate of entire planetary systems. The next time you see a headline about a new breakthrough from the James Webb Space Telescope, a lunar rover, or a comet flyby, remember, the smallest details, like invisible crystals hidden inside a grain of ice, can change the course of the biggest stories. The universe is filled with surprises, and each one brings us a little closer to understanding our place among the stars. In conclusion, the revelation that space ice contains hidden crystals shatters old assumptions and opens vast new frontiers in science and technology. It challenges our ideas about how life's building blocks are transported, forces us to reconsider the materials that underpin our digital world, and inspires generations of explorers on Earth and beyond to keep reaching for the unknown. While it may make the odds of life hitching a ride on a cosmic iceberg slimmer, it fills our imaginations with dazzling possibilities. Could there be forms of ice yet undiscovered, lurking in the coldest corners of the cosmos? Will we one day learn to harness these exotic materials for interplanetary travel, super-fast data transmission, or even the next leap in quantum computing? And here is a final, mind-bending fact. Just last year, scientists discovered a form of medium-density amorphous ice with the exact same density as liquid water. If you could somehow scoop up a fragment of this bizarre ice and drop it into your drink, it would neither sink nor float. It would simply hover there, defying all logic. The universe, it seems, always has another surprise waiting for us. If you found this story as captivating as we did, be sure to subscribe for more astonishing updates from the frontiers of science and technology. What do you think? Could these tiny hidden crystals be the key to unlocking the mysteries of life? Join the conversation in the comments below and let